Okay, good morning. Before I start, two announcements. Two announcements which both concern the next semester. The first announcement is so both about the winter semester 2005-2006. Now, one announcement is I want to announce our seminar, which we are going to organize in the next semester. And the seminar will be called Automated Termination Analysis. And the topic of the seminar is to discuss about methods to prove that a program is terminating and to prove this automatically. And now, as you all know, the halting problem is undecidable, so that won't work in general. But the goal is to solve this problem as often as possible. And we will try to do this for different kinds of programming languages. So we will do this for functional languages, for logic programming languages, and also for imperative languages. And also for terminal writing systems, which are something similar to functional programming languages. And in order to participate in the seminar, the participants should have heard one of the lectures, functional programming, program verification, terminal writing systems. So you, as the attendants of this lecture, are qualified to attend the seminar. And I think the registration for seminars will be next week via the internet. So you can register for all seminars, and then well, one possibility is to register for this one. And if you do this, then please, well, you can add some comments, and then add some comments which say that you are currently attending this lecture. And if you are also participating in the exercises, that is even better, because people who participate in the exercises are those that we prefer first, because then we know that people really actively attend the lectures. So this is something that might be interesting for you. And as I said, registration for all seminars will be, I think, next week, starting next Monday. The other announcement is that we're looking for HIVIs, student teaching assistants, for next winter semester for the programming, for the course Programmierung, which is the first year course. So this is the course that students start with. Probably you started with this one as well. And I'm going to give this course in the coming winter again. And the topic will be Java, Haskell, and Prolog. So as an attendant of this lecture, you can be sure that you know everything about Haskell that is required for this lecture, and much more. So you're very well qualified for the Haskell part of this lecture. But I guess you can also very well deal with the remaining parts. So if you're interested in leading a tutorial group for this lecture, then it would be good if you just contact me either after the lecture or send me an email. Okay, we look for HIVIs for Programmierung. Okay, these were the two announcements. Now, what did we do in the last lecture? In the last lecture, we finally defined how the domain should look like. The domain, we want to define the denotational semantics, and so our goal was to map every expression of Haskell to an object, to some mathematical object. And the question is, how do these mathematical objects look like? And we defined one big set, which we call DOM, and this set contains all these mathematical objects. So for all different types of expressions, we all map these expressions to an element of DOM. Now, how does DOM look like? DOM is defined recursively. So DOM has to satisfy this equation. This equation says this domain consists of, well, if an element is in DOM, then also all functions from DOM to DOM are in this domain. Well, not all functions, but also only the continuous functions. So this makes sure that whenever we have an expression of function type, then its value is contained in DOM. And moreover, if we have several objects from the domain, then also the tuple of this object objects has to be in the domain. So we also need to have things like the empty tuple. We need to have tuples consisting of 2 elements, of 3 elements, of 4 elements, and so on. And then finally, if the user defines his own data types, then the object that we map this to is again a tuple, but in front of this tuple, we write the name of the constructor. So for all constructors of arity n, we need an object of the form, first the name of the constructor, and then the n arguments. So these subsets, where we have first a constructor, and then n elements of the domain, they need to be in DOM as well. And so this is the definition of DOM. Now this we can ignore at the moment. So this is the definition of DOM. And now again, this is a recursive definition because DOM occurs on the left-hand side and it also occurs on the right-hand side. And now DOM should be the smallest set satisfying this. And then we can be sure that for every expression in Haskell, we can map it to a corresponding object of this domain. But this DOM, of course, also contains some objects that are superfluous because now we disregard all type information. So DOM will also contain objects like so it contains an object like suc0. And then this suc0, of course, since we build these coalesced sums and these lifts, they are always marked. So this is a marked version which occurs in constructions 1. Now constructions 1 are those tuples where the first element is a constructor of arity 1 and the second element is some other element of the domain. And this is again in DOM. Now these things make clear that a marked version of this occurs in constructions 1, and again it is marked, and then another marked version occurs in DOM. So this means this is the marked version of suc0, which occurs in DOM. But of course it also contains something like suc_true. And well, there is a Haskell expression which will have this as its semantics, namely, so this is the semantics of the Haskell expression suc applied to, we shouldn't say, let's say 0 here. Suc0, and we defined the data type nuts ourselves. So 0 and suc should be the constructors of this data type nuts. But there is no well-typed Haskell expression which has this as its semantics. So DOM contains a few elements too much, but that doesn't matter. So you can see that DOM also contains some objects which are not the semantics of any well-typed Haskell expression. But that is no principal problem. So now we have everything we need, and we can now formally define this function val, which takes a Haskell expression and maps it to an element of this domain DOM. So for example, if we apply val to the Haskell expression suc0, it should give us this. And now this is the next subsection, semantics, the semantics of simple Haskell programs. Now, as I said, we will define the semantics formally, but we will only do this for a very small subset of Haskell. And this small subset will look very restrictive, but in fact it is not restrictive because you can transform any Haskell program into a Haskell program of this subset. So this is a very reduced form of Haskell. So they are all legal Haskell programs, but many things that you can do in Haskell you are not allowed to do in these simple Haskell programs. But in the next subsection 223, I will show how to transform any Haskell program into a simple Haskell program. So if we define the semantics for simple Haskell programs, then in the end we have defined the semantics for all Haskell programs. Now, if we want to define the semantics of an expression, of course, in general, this expression may contain variables. Now, this expression, luckily, well, here's a suck and a 0, and we probably know what suck and what 0 means. But why do we know this? Well, because we somehow defined the meaning of suck and of 0. Or, in general, the meaning or the semantics of an expression, of a Haskell expression, obviously depends on the values of its variables. So if an expression contains variables, then if you want to know what this expression means, you need to know what value the variables have. So depends on the values of its variables. Now, let's look at an example. Now imagine the following example. This is a Haskell expression. Let x equal 3, so x should have the value 3 in the expression plus x2. Now, if we want to compute the semantics of an expression like this, what we will do is we will define the semantics in terms of the semantics of the sub-expressions. So we will first compute the semantics of plus x2, and depending on the semantics of plus x2, we can then compute the semantics of the whole expression. And to compute the semantics of plus x2, we first compute the semantics of x and of 2, and then we know how to compute the semantics of plus x2. But then, of course, to do this, well, there are some variables in here. There's an x, there is a plus. So the question is, what is the meaning of plus? What is the meaning of x? Now, when computing the semantics of the sub-expression plus x2, well, if we compute the semantics of this plus x2, then of course we have to take into account that we already know the value of x. Because in this, if we compute this, the value of this sub-expression, and it is in this let expression, we know that x is 3. Because x is in an environment where x is already bound to a certain value, 3. So whenever we evaluate an expression, we have to take into account the values of the variables, and when we look at this sub-expression, x has the value 3, and outside of this expression, x might have a different value. So when computing the semantics of the sub-expression plus x2, one has to take into account, one has to take the values of the variables into account. So here, the sub-expression is in an environment where x has the value 3. And moreover, so if we take this into account, then we know the semantics of x because it's 3. Well, plus is also a variable. So probably we defined plus by defining equation before. And in this defining equation, we said, well, plus should be the addition function. And so we also have to take the value of the variable plus into account. So it's similarly for the variable plus. Its definition should also be in the current environment. So maybe the value of plus is the addition function. So for example, the value of plus is the addition function. So in general, we can only define the semantics of an expression if we know what the values for the variables are. So to define the semantics of an expression, we need to know the values of all variables in the expression. The values of the variables. And to do this, we define the concept of an environment. An environment is simply a mapping from variables to values. So an environment is a function which assigns a value to every variable. So an environment is a function which assigns values to variables. And so we can only define the semantics of an expression with respect to some environment, which assigns values to variables. And the semantics of an expression can only be defined with respect to an environment. So obviously the semantics of plus x2, if the value of plus is the addition function and the value of x is 3, then the value of plus x2 is 5. But if we are in a different environment where x doesn't have value 3 but value 4, then the semantics of plus x2 is not 5 but 6. So clearly the semantics depends on the values of the variables. Now let me define formally what an environment is. So this is definition 224. Environment. So if we have a Haskell program with the domain DOM, a function row is an environment if a row is a partial function which maps variables to values. So it's a function from variables to values, so to elements of the domain DOM. Here var is the set of all variables. And the requirement is that this function may only be defined for finitely many variables. So it is almost always undefined. If row is a partial function which is only defined for finitely many variables. For finitely many variables. And since it's only defined for finitely many variables, we can also write it in a special way. If row is only defined for let's say, variable 1, variable n, and if rho assigns to variable I the value di, then we can also write down this function, rho, this environment, simply by writing it as first the list of all, well, either by a set of pairs, so variable 1 is replaced by d1, variable n is replaced by dn, or sometimes we also write first the tuple of all these variables and then the tuple of all the values. So both notations are used. So this looks very similar to the way one writes substitutions. So if you think of substitutions in logic, same idea. You replace variables by terms. You only do this for finitely many variables. Therefore, you can write it in this way. So we simply say this variable has value d1 and this variable has value dn. We just write it like this. And the set of all environments is called env. So the set of all environments is denoted env. Now sometimes we have to modify these environments. You can see this up there in this let expression. If we have the sub-expression plus x2, we would normally, and we want to evaluate this in some environment, we would check what is the value of plus, what is the value of x. But if we have to evaluate it in such a let expression, then the value of x is modified. Now suddenly x has a different value, namely 3. And to perform this modification of environments, we define the following notation. So if we have two environments, row 1 and row 2, then the environment row 1 plus row 2 is like row 2 for all elements, for all variables where row 2 is defined. And otherwise it's like row 1. And like row 1 otherwise. So in other words, this environment, which is row 2 extended by row 1, if we apply this to some variable, so we want to know what is the value of this variable in this new environment, then we first look into row 2. If row 2 is defined for this variable, then that's the value. So it's row 2. If row 2 is defined, and otherwise it's the value that is assigned by row 1. So, and this is going to happen. If we have a let expression like this, then we used to have some expression, some environment like row 2, but now we modify it by assigning x a new value 3. So this will be the environment that assigns the value 3 to x, and this is the environment that we had before. We will see this in the formal definition later on. And now at the very beginning, if you start writing your Haskell program, then of course there are some things that are predefined. So for example, something like map or take or the double plus or 1 plus or times, things like that are predefined in Haskell. So some variables already have a meaning, even if we don't start writing any programs. And therefore we have to start with an environment which is not completely empty, but predefined variables already have a certain meaning. And this environment where the predefined variables already have the correct meaning is the initial environment, and we denote this by small omega. So let small omega be the initial environment And what does this initial environment do? Well, it assigns to every variable which is predefined in Haskell the respective meaning, which assigns to all predefined variables of Haskell the respective value. So for example, what happens for the predefined variable plus? Now this is a predefined function in Haskell. So it's a variable which has it's a variable plus it's a variable, an infix variable, and it has a meaning already in Haskell. So even if you don't define anything yourself, you can already use this function. So it already has a semantics. And its semantics is given by this initial environment. So the initial environment, in this environment, plus will be mapped to some value. What is the value? The value is a function from DOM to DOM to DOM. And how does this function look like? So let's apply this function to two elements from DOM, and then we define what the result is. So if x is one element of DOM and y is another element of DOM, then what is the result? Now DOM contains many things. We can see how DOM looks like. And now the meaning should be the addition function. But of course, we only need this if the two elements that we apply plus to are integers or floating point numbers. And we restrict ourselves to base types where we have int, float, booleans, and characters, and you can only apply plus to two integers or two floating point numbers. So the meaning should be x plus y if both x and y are integers or x and y are floating point numbers in construction 0 in DOM. So these are the marked versions of these integer numbers or floating point numbers that are in this domain DOM. And otherwise, it's undefined. So all these functions in here are strict. So whenever one of these arguments is undefined, then the result is undefined as well. So all these functions that are the functions that predefined variables are assigned to, these functions are strict. So if one element is undefined, then the result is undefined as well. Okay, so we now have an initial environment, and this initial environment gives us the meaning of all the predefined variables. If we later on add definitions, then the environment will have to be modified, because then there are more variables which have a meaning, and to modify environments we need this plus operator. And then we can now define the value of an expression under a certain environment. So we assume that we know the meaning of all variables. This is simply predefined, or we add some definitions, and then we can say what the meaning of an expression is. Function value, and well, when I discussed the motivation for value in the beginning, I said, well, this is a function which takes an expression and returns an element of the domain. Now that's not true, because that's almost true but not quite true, because the expression may contain variables. And now how do you want to define the meaning of x? Well, you don't know. It depends on the environment. So in fact we need two inputs. We need an expression and we need an environment, And then we can say what the meaning of this expression is under this environment. So if the variables have certain values, then we can say what the meaning of an expression is. So as I said, the semantics can only be defined with respect to an environment. Now, our goal is to define this, and as I said, we will not do this for full Haskell. We will only do this for a subset, a very small subset of Haskell, which, however, is powerful enough to express everything. And so, to simplify, the definition of val, we only regard a small subset of Haskell. But in fact, every Haskell program can be transformed into a Haskell program on the small subset. Every Haskell program can be automatically transformed. So can be transformed automatically into this small subset, and we will see how to do this in section 223. Section 223. So this makes clear that many concepts of Haskell are just what is called syntactic sugar. So it makes life easier and programs look more readable, but you don't really need it. You can already write every program. You have a Turing-complete language if you only take a very, very small subset. And we will, in fact, make this subset even smaller. So we have something like this. Here we have full Haskell. And the subset that I will show you is simple Haskell. But you can automatically transform every program from here into a program from there. So every computable function can be computed in simple Haskell. And then in the next chapter, we will make this even smaller. And so then the question is, in this chapter, how to implement Haskell. And we only implement another very, very small subset of this, the so-called lambda calculus. But again, every program in simple Haskell can be transformed into a program, well, a term of the lambda calculus. And even the lambda calculus, which is a very, very small language, so the definition of this language easily fits into one line, but you can make it even smaller, and then you get the pure lambda calculus. And in this pure lambda calculus, again, you can already write every program that you want in the pure lambda calculus. Of course, programs become less and less readable. So programs in the pure lambda calculus are absolutely unreadable. So I will show this to you later on, and we define something like addition or multiplication, the pure lambda calculus, but you would never recognize that this is addition. Now, lambda calculus is already pretty unreadable, but a bit more readable. This is still quite readable. This is hard to read, but good for implementation. This is only interesting for theory. But you can make things smaller and smaller, and this is still a complete programming language, but it's no fun to program in this language. So this is big fun, but this is less fun. Okay, so for the semantics, we will do this. We will look at this language, and for the implementation, we look at this language. And we will not look at this language except for, well, I will show it to you so that you know it, but we will not use it for semantics or implementation. So this shows that a lot of Haskell is syntactic sugar. So what is simple Haskell? How does full Haskell differ from simple Haskell? Well, we do certain restrictions. What are the restrictions for simple Haskell? So, first restriction is, normally in a Haskell program you have many, many, many declarations. You declare a function square and a function, I don't know, well, many, many functions, and all these functions have many function declarations. Now we don't do this, we only allow one single declaration. And moreover, not a function declaration, but just a pattern declaration. So only one single declaration. And the declaration must have the following form: variable equals expression. So normally here you can also have variable and then many patterns. So if you want to declare a function with n arguments, you would have the name of the function and then n patterns. Now we don't do this anymore. Our functions have just this variable on the left-hand side, no patterns. If you want to have patterns, you have to do this via lambda expression. And just one single declaration of this form. So not many functions, fact and times and plus, just one. So this is a rather hard restriction. The next restriction is not so hard. We don't use predefined lists, but we can use user-defined lists. So this is just to avoid treating this case of the special notation separately. So we may have user-defined lists. So they are equivalent to the predefined lists. Then the third restriction is normally you can write applications of the form expression 1 is applied to expression 2, and then the result is applied to expression 3 and to expression 4. And we don't write this anymore. No n-nary, so n times you apply expressions to each other. No n-nary applications of the form expression 1 is applied to expression 2, is applied to expression n. Only binary. Now this is also no restriction, because this thing here is equivalent to, first you apply expression 1 to expression 2. This is a binary application. And then you apply this thing to expression 3. And then you apply this whole thing to expression 4 and to expression n in the end. So you have to write this and not this. This is really just syntactic sugar. We just add these parentheses. This means the same thing as this. So 2 and 3 are no real restrictions. 1 looks pretty hard, this restriction. The main restriction that we have is we don't have pattern matching. And this can already be seen from restriction 1, because normally you would have these patterns here, and then they would be used for pattern matching. Now, there's also a different form of pattern matching. You can use the case construct in Haskell, and case does the same thing. Case also does pattern matching. Therefore, we do not allow the case construct anymore at the moment. No case construct. And then lambda expressions may only have the form lambda and then variable arrow expression. So normally you can write here a pattern. We don't want pattern matching. So instead of an arbitrary pattern, you can only write a variable, and you can only write one variable, not many variables anymore. And then finally, we have no where. Now this is again not a big restriction, because we have let and where are equivalent. So whenever you write something with where, you can also write it with let. So to ease our treatment, we only regard let. No where, but we have let. So most of these are harmless restrictions, like this one, or this one, or this one. And the other ones are restrictions which mainly say we don't have pattern matching. So the main restriction is we have no pattern matching. This is a real restriction, and how we can transform a Haskell program with pattern matching into a Haskell program without pattern matching is something we will discuss about later. So the definition for simple Haskell expressions is as follows. I put it already on the slide, and I wipe the board. Okay, there are two more restrictions that I forgot to write down here, but they are on the slide. So this is already a restriction that I mentioned before. We make this restriction now in general. We do not regard type synonyms anymore. So these are just abbreviations where you start a declaration with the keyword type and not with the keyword data. This one is a real restriction, no type classes. So if you are fond of monads, then unfortunately I have to tell you that you cannot use monads anymore if we exclude type classes. So unfortunately we cannot look at monads in the rest of the lecture anymore since we exclude type classes. That's a big pity, but okay, it makes life harder, and therefore we exclude them to simplify the treatment here. So no type classes. That's another, I should add this. So no type synonyms. So this means declaration with type and no type classes. And this means that the grammar for expressions now looks like this. So if you compare this with the definition of this grammar in full Haskell, we have the following differences. Here you normally have an application of many expressions to each other. Now we just have an application of one expression to another. Here we have just one single declaration in the let block, so not a sequence of declarations, and it's just one single declaration of the form variable equals expression. So that's the idea. A program has just one single declaration, and this is a pattern declaration of this form. And the lambda expressions just look like this. There is no where here, and there is no case here. This has been dropped. Now this is the main difference. Now maybe you can think about how to program, say, the factorial function in simple Haskell. As I said, every Haskell program can also be written in simple Haskell. So pattern matching is not allowed, but you can still write it. So how would you, for example, program the factorial function in simple Haskell? So this is all you may use. And while you think about this, I wipe the board. Okay, how would one program the factorial function in simple Haskell? Now let's say it's called fact. Now normally you would probably like to write something like this. Fact of x equals something. Or probably even fact of 0 equals 1 and fact of something else equals something else. Now this is not allowed. First of all, you may only have one single declaration. Oh, not two. And then second, this is also not allowed. You may not have more than one variable on the left-hand side. So if you want to declare fact, then fact is the only thing on the left-hand side, no x. Oh, now you can try to formulate this. I can only give you one single declaration, and this is the left-hand side. So how will the right-hand side look like? No, it's not so difficult. Right. Right. Yeah, let me do it with 0. I always defined the factorial of negative numbers to be 1. So let me do it like this. So now, even for negative numbers, it's 1. Right. So x times fact of x minus 1. So in fact, the definition of fact that we already used for illustration when we illustrated the definition of the semantics, this is simple Haskell. So this is an example for simple Haskell. So you can define factorial in simple Haskell. You would have to do it like this. Okay, now let's try to define the semantics. And well, normally you would have to define the semantics of an expression within a program. Now, in order to avoid this, we will say, well, a program in the end just consists of something like this. So this is a program. Programs in simple Haskell cannot be much longer than this. They have just one single declaration. So instead of defining the semantics of an expression like, say, fact3 in a program which contains this declaration, in a program which contains containing the definition of fact. Instead of doing things like this, we will always just assume the program to be empty and then rather look at a let expression where we make this declaration local. So instead of doing this, we define the functions, or the function, since there's just one function in simple Haskell, locally for the expression. So in other words, we instead regard the expression of the following expression. It's an expression where we write the declaration of the program into a let declaration. So it's let fact be lambda x, and now this stuff here. So if then else. And then in this expression that we want to investigate. So we want to know the meaning of fact3, but fact is already defined, and now we put this fact declaration into a let block. We regard the semantics of this in the empty program. And by doing this, we never have to care about programs again. We only care about expressions. We want to evaluate, we want to know the meaning of an expression, so we would like to know the meaning of this big let expression. Of course, the meaning of this should somehow be 6, because fact3, if fact is the factorial function, then the factorial of 3 is 6. And so this is one thing we have to keep in mind. And the other thing we have to keep in mind is we only define the semantics for well-typed expressions. So we assume that our expression is well-typed. How to check this, we will see later on. But then we don't care about types anymore. We are sure our expression is well-typed. So we only define the semantics for well-typed expressions. So how to do type checking automatically, this will be done in chapter 4. And now, last prerequisite we need before we can really start defining the semantics is the concept of a free variable. As I said, if we have an expression and we want to define the semantics, we need to know the values of the variables. Well, we don't need to know the values of all variables, only of those variables which are free, which are not bound by a lambda or by a let. So if you look at this expression, well, the meaning of fact is already given by this declaration. So in this suffix, so in this expression, fact is not free. Fact is bounded by this declaration. But if we would have let fact be this here in fact of y, then y would be free. And so in order to give the meaning of this whole expression, we would need to know the value of y. So it makes sense to distinguish between free and bound variables. So semantics can only be given with respect to an environment which is defined on all free variables of the expression. That is defined on all free variables of the expression. So as I said, an environment is a partial function, so it is not defined on every variable, but it should be defined on the free variables of the expression, on all free variables of the expression. So what does it mean to be a free variable? Well, that is something we can easily define. So free variables. So what we define is, for every simple Haskell expression, so every expression of simple Haskell, every expression that is built according to this grammar, for every simple Haskell expression, exp we define the set free exp, and this is the set of its free variables. And as I said, these are all the variables that are not bound by a let or by a lambda. So let's simply look at all the cases. You can see the grammar over there. So let's do one expression after another. Now the easiest expression is simply a variable. Now in this expression, this variable is not bound by a let or by a lambda. So the set of free variables of this expression is this variable. Now if you have an expression which is a constructor, a user-defined constructor, or an integer or a floating point or a character, then there is no free variable. So for constructors, for integers, for what else do we have? Floating points and characters. And for characters, there is no free variable. Oh, by the way, I forgot to give definition 225. So definition 225 are simple Haskell programs. So if you wonder why do we go from 224 to 226, the reason is that this should have a number. So simple Haskell programs are definition 225. Okay, let's continue with free variables. Now, what is the next possibility? The next possibility is we can have tuples. What are the free variables of a tuple expression? So if we have a tuple expression 1, comma, expression n, well, the free variables, we simply take the free variables of expression 1 and those of expression 2 and those of expression n and unite them all. So the free variables of expression 1 united with the free variable of expression 2 and of expression n. And similarly, if we apply one expression to another, the same thing happens. We just unite the free variables. So if we take expression 1 and apply it to expression 2, then the free variables are those of expression 1 plus those of expression 2. I mean, free variables are those variables which are not bound by let or lambda, so here we just have to look at the sub-expressions. And similarly for, what is the next thing, if? For if we have if expression 1, then expression 2, else expression 3. Again, we just unite all the free variables in 1, 2, and 3. Now we have the only two interesting cases, let and lambda. So if we have a let expression of this form, let variable equals expression in expression prime. Now, what are those variables in this expression that are free? Well, we take all the variables in expression prime, all the free variables in expression prime, and all the free variables in expression exp, but var is not free, because var is bound by this let expression. So we take all these free variables, but without var. So the free variables in exp united with the free variables in x prime, but without var. So all those variables that are not bound by let or by lambda. So for lambda, we get something similar. If this is our expression, let var arrow exp, then the free variables are those of exp, but not var. So this is the definition of free variables. And now, as I said, we can now start defining the semantics. But we define the semantics with respect to an expression, and this expression has to, with respect to an environment, and the environment has to be defined on all free variables. So we now start, we define this value function. And as I said, this value function takes two arguments, exp, an expression, an environment, and then it gives us a value of the domain. And we typically write this as follows. So we write the expression into this strange double square brackets, and we write the environment beside this. So val is applied first to exp and then to row, but for well, in the literature, typically you write these strange double brackets around this exp. So this makes clear, normally this is the value of x, but, well, in the environment row. So this is the value of expression exp in the environment row. And as I said, the environment has to be defined on all free variables of exp. So here the prerequisite is row has to be defined on all variables of free exp. And now the question is, how do we define this? And we do this again step by step by looking at all different expressions. So we look at this grammar, and then for each possible expression, we now say how this value looks like. Okay, so let's start. Now the simplest form of an expression is just a variable. So what is the semantics of a variable in this environment? Now, the semantics of a variable only depends on the environment and nothing else. So if you want to know the semantics of this variable, we have to look into the environment, and the environment will tell us all that we need. So the semantics is simply row of var. So the semantics only depends on the environment. Here's an example. Suppose we have an environment if we have an environment row with where the variable x has value 2, then what is the value of x in this environment? Well, it's simply, so the semantics of x is row of x, so the semantics is 2. Of course, in constructions, so it's in the subset constructions, and then it's in DOM, so it's a marked version of it. I will often omit this to ease readability, but if you want to be very precise, you have to do this. Or, as another example, what is the value of this variable plus in the initial environment? So this is a variable, a predefined variable. So the meaning of this is predefined. Well, and we are interested in the value of this variable in this environment. So luckily, this is defined in this initial environment, and it's the addition function. So this is the addition function, since plus is predefined in the initial environment. Now, so this holds for all variables, including variables from the subsets integer, float, and character. Now what happens if we have a constructor, a user-defined constructor? So let's say we have something like this. Constr 0, and this constr 0 comes from con 0. So this is a constructor of arity 0. Now this can, for example, be a user-defined constructor like the constructor 0 with capital Z, or it can be a constructor, a predefined constructor of type int, something like 0, -1, +1, -2, +2, or of type float, or of type character. Now, the semantics of this, now we know what to do with data objects, which are, for example, user-defined. We map this to a value which normally takes the name of the constructor and then the values of all arguments. Now here there are no arguments because this is of arity 0. So this is just the name of this constructor. So it is just constr 0. Of course, the marked version, which is in constructions 0 in DOM. So for example, if we want to know the value of the number of this Haskell expression in any environment, now this, for those variables, only the environment is important. For constructors, if the constructors have no arguments, then the environment is completely uninteresting. This only depends on, well, here is the value of this is just itself. So the value of this is just 5, but it's the marked version, which is in constructions 0 in DOM. So in other words, constructors of arity 0 are interpreted as just themselves. So their meaning is just their name. If we have constructors with more than one arity, so something like this. So a constructor of arity n, and n is greater than 0, then what is the meaning? Well, if we later on apply this constructor to arguments, then we want to get an object which is a tuple. So the first element of the tuple is the name of this constructor, and the other elements should be the meanings of the arguments. So the result should be a function f, and f is a function. So f basically creates constructor ground terms. So if we apply f to n arguments, so let's apply f to n arguments d1 to dn from the domain, this should then create the desired object. So it should be an object which is a tuple. First component of the tuple is the name of this constructor, and then the remaining components are the arguments of f. So the meaning of such a constructor of arity n is a function which waits for n elements of the domain, and if it gets these n elements, it will produce a tuple containing these n elements and the name of this constructor. So, and this of course is in constructions n in DOM. So let's look at an example. So assume we defined the data structure nuts with the constructors 0 and suck. And then what would be the value of the constructor suck? So here we defined a data structure data nuts as 0 or suck, where suck takes an argument of type nuts. So the value of this expression is a function. It's a function f, And this function waits for another argument of the domain, D. And if it gets this D, it will give you back a tuple consisting of the name of this constructor, suc, and the argument over here. In constructions 1 in DOM. So constructors are simple. The meaning of constructors is a function which waits for arguments and then builds a big term or a big tuple out of it, which starts with the name of this constructor. Now, we've handled the first 5 cases. Now the next case are tuples. What is the value of a tuple? So we want to know the value of the tuple x1 ... xn. Now, what is the value of this? It's simply the tuple where the first component is the value of x1, in some environment row. The second is the value of x2, and so on. So it is the tuple. First element is value of x1. Next one is the value of x2, and the last one is the value of xn. So if you want to know the value of a tuple, compute the values of the components, and then the value of the tuple is the tuple of these values of the components. And in the special case where n is 1, so if you want to do this, then the meaning is the same as if you just ignore these parentheses. So there is no difference between, so the semantics of this here and this here is the same. This means Haskell makes no difference between tuples of one component and the component itself. And this, of course, is in tuples in DOM. In tuples n. Since these are n tuples. Okay, so this is how we deal with tuples. Now let's look at function applications, or at applications in general. What is the meaning of this here? So this is an expression where expression 1 is applied to expression 2. Now, if this is well-typed, and we only define the semantics for well-typed expressions, then the type of expression 1 is a function type. And that also means that the meaning of expression 1 will be a function from DOM to DOM. So let's assume that the meaning of expression 1, this should be a function. So this should be in functions in DOM. So in other words, f goes from DOM to DOM. So if we already know the meaning of x1 and we know the meaning of x2, then we can say what the meaning of this bigger expression is. Namely, we take the meaning of x1, which is this function f, and apply it to the meaning of x2. So it should be f applied to the meaning of x2. So what would be an example? Let's look at the following. Let's look at the meaning of this expression here, suc0. Now here we have this. These are two expressions, the expression suck and the expression 0. And we now want to compute the meaning of this whole big expression. So how do we do this? Well, we first compute the meaning of suck, and the meaning of suck we have already up there. So the meaning of suck is a function, f, which waits for an object of the domain, and then it gives us this tuple, suck, comma, d. D was the argument of f. So it's this function f up there applied to the value of 0. Now I will drop these in constructions in DOM to make life easier. Now what is the value of this? Now 0 is a constructor of arity 0, so the meaning of this is just its name. This is just the name 0. And what does f do? We can see it up there. F applied to d gives us the tuple suck, comma d. So this gives us the tuple suck, comma 0. And this is, as I illustrated before, if we have constructor terms built with this constructor, suck, then the meaning is a tuple where the first component is the name of this constructor and the remaining components are the values of the arguments. And this is exactly what happens here. So, I mean, this is all not new. This just recapitulates what we have defined before, but now we can finally write it down formally. All the ideas that are behind this we have discussed in the preceding lectures. Now, what's next? There's an if expression. That's, again, easy. So the semantics of something like this. If x1, then x2, else x3 in some environment rho. Now, what should the meaning of this be? Well, we now have to define this. I mean, we defined the semantics of this programming language. So we now make clear what all the expressions in Haskell mean. And so if later on someone wants to implement a compiler or interpreter, then he only has to look at this definition and then he knows everything. So we have to tell him what if means. I mean, he probably doesn't know, so we must make clear what if means. And of course, we know what it should mean. So what would you suggest? What should the value of this be? And I mean, this definition always works recursively. So in order to compute the value of this big expression, we first compute the values of x1, x2, and x3. And then, depending on their values, we can say what the value of this big expression is. Well, there are basically several possibilities. Now, what do? We first compute the value of x1, obviously. If it's true, then the result is the value of x2. If it's false, then the result is the value of x3. So it's the value of x2 if the value of x1 is true in constructions 0 in DOM. So this marked version, which is in DOM, is the value of expression 3 if this thing is false. Well, and there's another possibility. In fact, there are many other possibilities. But if this is well-typed, then there's just one more possibility. So if this is well-typed, then this is an expression of type bool. And so what can the value of this be? It can be true, it can be false, but it can also be bottom. If it's bottom, then the value of this whole expression should be bottom. Okay. So now we come to the most interesting case. So this is the most problematic one. So now we want to know what is the value of an expression with this let statement in some environment rho. Now let's first look at an example, and we first regard the easy case. So case 1, you can probably imagine what the problem is. The problem is that this declaration here can be recursive. So if you're unlucky, then this is not something like let x be 3 in some expression, but it can be something like the factorial definition, which is recursive, and then we are at the point where we have to define the semantics of recursively defined functions. I mean, all this stuff that we discussed about with fixed points and so on somehow has to pop up in this definition, and it will pop up here. So there's no chance to get around it. It will pop up here, but let's first look at the easy case. So the easy case is no recursion. So no recursion means the variable does not occur in the free variables of x. Then we do not have recursion. Here's an example. Let x be 3 in x plus y. Now this is not a recursive definition. X equals 3 here. So let's see, what should the value of this be in an environment rho and let's say what are the free, well we said that the free variables in an expression have to be defined in this environment. So the free variables in this expression are y and plus, but not x, because x is bound here, where rho is defined on the free variables, and the free variables are plus and y. So how should it be defined? Let's say rho of plus is the same as the meaning of plus in the initial environment, so it's the addition function, and rho of y, let's say rho of y is 2. So rho doesn't have to be defined on x, and even if it is defined on x, that doesn't really matter, because in this expression x should have the value 3, no matter what the value of x might be in this environment. So how can we define the meaning? Well, we have to take this into account. That's the big problem. And in order to take this into account, what we will do is we will modify this environment. So we overwrite the current meaning of x by 3. So we make sure that, so we modify this environment rho into a new environment, rho prime. And in rho prime is almost like rho. The only difference is that now x has the value 3, but the values of plus and of y are still the same. And then in this new environment, we evaluate x plus y. That's the idea. So define it as the value of x plus y in a new environment rho prime, where rho prime only differs from rho by assigning to x the value of this here, the value 3. So more precisely, we would then say the value of such a non-recursive let expression, let var equals x in x prime, that the value of this should be the value of x prime, but not in the original environment, but instead in a new environment which differs from the original one by assigning to this variable the value of x. So So this here is this new environment. What does this environment do? Well, this plus means, first look into this thing on the right-hand side. So it will, to this variable var, it will assign the meaning of exp, and to all other variables, it will do the same thing as row. And so the result, the meaning of this let expression is the meaning of x prime, but in a different environment, which is almost like the original one. The only difference is this variable now has the meaning of exp. Now this is very nice, but it doesn't work for recursive declarations. So the problem is, case 2, if we have recursion, and we had this example already, we had this declaration, let fact be the factorial function, so if x is less than or equal than 0, it's 1, and else it's x times fact x minus 1 in factorial of 3. And now the problem is, here we have this recursive declaration, so we cannot say we take an environment where fact has the meaning of this stuff on the right-hand side, because this stuff on the right-hand side contains fact again, and fact is a free variable. So that's not the correct meaning. What we mean here is something different. And as we already discussed, the meaning of something like this, of such a recursive definition, is that so the meaning of this recursive definition is the variable fact should be assigned to fact. We want to assign the smallest or least fixed point, or the smallest solution of this equation. The smallest solution of this equation means it's the least fixed point of a function ff which transforms the left-hand side into the right-hand side. The least fixed point of a function ff which looks like this. So ff takes an element of the domain, so this is an element of functions in DOM. So this is an approximation to the factorial function, and it gives us back a better approximation. So it should be a fixed point. In other words, the value, this should be the same as the value of the right-hand side, provided that fact has the meaning d. So in other words, it should be this. It should be the meaning of the right-hand side. So if x is less than or equal than 0, then 1, else x times fact x minus 1. But in an environment where fact is assigned, where fact gets the meaning d. So in other words, this means ff is a function which maps a function d to another function d, and this new function d is what we get by taking the value of the right-hand side of this declaration, provided that fact has the meaning d. So what this does is exactly the same thing that we discussed before. ff is a function which transforms one approximation to fact into another approximation to fact, which is better, and we look for the least fixed point of this function. And if we know this, we can now define the semantics for let expressions in general. So the semantics for let expressions in general is this. Let var equals exp in x prime should be the following thing. It should be the semantics of x prime, but not in the original environment, but in an environment where we change the meaning of var. And now for non-recursive declarations we said, well, var just has to be assigned the meaning of exp. For recursive ones we said var has to be assigned be assigned the least fixed point of a certain function, namely a function which transforms this left-hand side into this right-hand side. And let's write it down for recursive declarations. So var has to be assigned the meaning, the least fixed point of a function f, where f of d is the semantics of exp under an environment rho, where var is assigned d. And I will illustrate this again in the next lecture, and we will see that this also works for non-recursive declarations. So if we have a non-recursive declaration over here, then this gives us exactly the same thing as what I illustrated in case 1. So we can really always use this definition, which only treats case 2, because case 1 turns out to be a special case of case 2. Okay, we will come back to this in the next lecture on Friday.